Chapter 11, Infinite Sequences and Series. You'll see a lot of changes from this point on. One glaring difference is the tempo. I'm going to slow down quite a bit. I assigned 5 weeks in Chapter 11 alone. Counting in the review session, it's going to be 6 weeks. That's a lot of weeks for a single chapter. And consequently, I'm going to go a little bit more in-depth, and I have to. The second difference is the content. The content of Chapter 11 will look very different from that of, well, the rest of the textbook. We are dealing with discrete systems. Here we go. We begin with the concept of a sequence. A sequence can be thought of as a list of numbers written in a definite order, A1, A2, A3, and so on. Each number in this list is called a term. A1 is the first term, A2 is the second term, and so on. In general, we have nth term, An, which we also call the general term. Once we have the general term, we can find the next one, An plus 1, which we call successor. A successor, that's an interesting concept. We have no such a thing for real functions. If you have f of x, for example, what is the next function value? Or if you have a real number x, what is the next real number? There is no such a thing. For natural numbers here, on the other hand, 1, 2, 3, 4, and so on, there is a next natural number for each natural number we have. For example, n is 4. Then what is the next natural number? That's 5. There's nothing in between. So if you arrange them, then we have a discrete system. Consequently, we are dealing with much simpler objects than real functions. So if you have something simpler and something easier, then the trade-off is we can afford to go a little bit deeper. And in the end, how does it balance? Well, traditionally, it's used to balance that in harder side. I've been teaching in college level since 1994, and I've taught Calculus 2 many times. Each semester, this is where the students struggle the most. Well, I want to change that a little bit, so I put a little bit more time here, and I sacrifice some unimportant topics here and there, like snipping out the entire chapter 8 and throwing away some sections that are too much applicationally oriented. Instead, let's focus upon chapter 11, and yes, as you have been warned, we're going to go a little bit in depth here. And well, the very first step is going to be a little bit different here. The way our textbook did was that vague description about a sequence. It can be thought of, blah, blah, blah. Instead, let's define it more precisely, like this. This is the direction I selected. A function, A, defined in a set of natural number n, 2, set of real numbers r, is called a sequence. We know about functions, right? So this is a precise definition, not a vague description like the way they did in the textbook. Okay, it's a function, so we have to have the domain and the target. The target is a real number system, and you can change that to something else, for example, complex numbers, if you will, and then pair or triple of real numbers. You can do all those. And the domain is traditionally the set of natural numbers, but sometimes you can start from 0 and take the set of whole numbers, W, instead. So kind of like this. So if you have function f of x, well, that's traditional function, real function. But instead of f, g, h, it is tradition to use a, b, and c for sequence, so that. And then for real number system, x and y, those kind of things are common. But instead of those, we are using m and k, things like those. Sometimes ij. And we have things like this. A of 2, oops. Kind of like this. And it is tradition to express these parentheses as subscript. as far as sequences are concerned. So that's just notation issue. In terms of definition, nothing changes. It's a function. By the way, if you are a programmer and if you have to do some programming with C or some other programming software, C++ or things like those, you'll have to use those parentheses back again, sometimes brackets. Let's go over to some examples. What if we have a general term given? Is it possible to find out the list? Well, that's too easy. Just plug in n equals 1, 2, 3, and so on. Then we have a list. To go backwards can be a little bit trickier, so you have to have some experience. In the first problem, it is not too bad. We have negative 1 to the nth power. Oh, excuse me. We have to start from the right. Okay, from the right. Negative, positive, and so on. We have alternating sign. So negative 1 to the nth power seems good. If we have to start from the negative, negative 1 to the nth power. If you have to start from the positive, then you have to use negative 1 to the n plus 1 power or something like that. And then denominator is 1 bigger than the numerator, so n over n plus 1 makes perfect sense. But if you have something like this, it's not easy to get this one from just this pattern. Sometimes you'll have to do that, but, well, at this level, we are not going to consider those kind of things too much. Now, another effective tool to describe or define a sequence is through a recursive relation, kind of like this. First term is given, A0 is given, and then a relationship between the general term and its successor. So how do you do that? 2an plus 1 is equal to, if I flip this an to the other side, this is what you get, right? So if I divide this 2 away, then we can determine the successor from the general term. So if you plug in A0 right over here, then this computation will give me A1, and from A1 we can find out A2, from A2 we can find out A3, and so on, as we see over here. So we can cover everything. In general, it turns out that AN is something like this, but this is something you're going to be doing in, I think, Math 3410 or 3420, differential equation 102. This example is a famous example. It is called Fibonacci sequence. The first two terms are given, f1 and f2, and then there's a recursive relationship between three terms. So from f1 and f2 we can find out f3. From f2 and f3 we can find out f4, and so on and so forth. So f3, f4, f5, we can find everything. And for some really strange reason, the general term becomes something like this, and magically everything will just cancel out and we get integer values. By the way, this quantity over here, 1 plus square root of 5 over 2, is called a golden ratio. There is a definite relationship between Fibonacci sequence and golden ratio. If you want to find out a little bit more about Fibonacci sequence and golden mean, please just go over to internet like YouTube and then just type in Fibonacci, then you can find out a lot of resources. Oh, I nearly forgot. The opening picture of chapter 11 shows you a certain surfer and this wave pattern is developing partly based upon Fibonacci sequence. It's amazing, but that's true. That's why I think the textbook author chose this picture. Okay, let's go back to the course material. Fibonacci sequence and recursive relations are interesting, yes, but those are not the most important topics for our purpose. Our purpose here is calculus, so the most important topic for us is limit. We say a certain sequence converges to a certain real number L if the general term gets closer and closer and closer, arbitrarily closer to L. And if that doesn't take place, then we say the sequence diverges. One good way to visualize that is through horizontal asymptote. Let's see how our textbook author decided to visualize. Yes, here are some pictures of convergence. We have horizontal asymptote at y equals to L, And if you have graph of a function limited at infinity, then we have horizontal tangent like this, horizontal asymptote like this, excuse me. And for discrete sequences, then we have bunch of dots, but in the end, horizontal asymptote. That's a visualization for limit. Okay, limit concept, difficult to establish, but easy to understand. Limit rules, let me classify things like these. First, trivial limit rules. Constant k remains constant. Duh. This is another tautology. If n goes to infinity, then n goes to infinity. Duh, another tautology. This one, on the other hand, is not duh at all. This is important, and this is very difficult to prove. 1 over infinity becomes 0. Seems like pretty simple, but it turns out it is very difficult thing to prove. I think you'll have to prove it in either Math 3000, Real Analysis 1, or 3610, Real Analysis 2, depending upon your instructor. I usually do it in Real 1. It's related to something called Archimedean property. Okay, some more limit rules. Sum of limits. Multiplication by certain real number, k. Product of two limits. And we have quotient of two limits, where denominator is not 0. If you have a continuous function, then you can slip the limit inside, and then we can have this kind of rule. So we can slip limit inside any radical, and inside the exponential, and many more, inside logarithm, inside trigonometric functions, and so on and so forth. Just be careful about the domain of that function. Okay, final rules. We have inequalities, so if one sequence is bigger than the other sequence, then the limit has to be bigger, of course, common sense. And then the squeeze theorem. If a sequence Bn is squeezed by these two sequences, An and Cn, and An and Cn share the same limit, then Bn is squeezed by these two, and it has to have a limit, and it has to have the same limit, L. Final comment. Here, if you have strict inequality, does it mean limit of Bn is strictly bigger? The answer turns out you know. It is possible to find out examples where we have the same limit, even though right-hand side is strictly bigger. Kind of like this, 1 over 2n versus 1 over n. In that case, 1 over 2n and limit of 1 over n the same. So strict inequality, well, does not translate there. Well, okay, we have a couple of minutes left, so let's talk about monotone sequence theorem. I'm not going to prove it, of course. I'm simply tell you what it is. And this is naive version of monotone sequence theorem. Any bounded monotone sequence converges. We're going to use that in some of the examples here. And one of the more important application of this monotone sequence theorem is decimal expansion. Let's see, in grade schools we learned, you must have learned that irrational numbers with no pattern, irrational numbers are decimal expansions with no pattern. And yes, that's true, but then again you have to answer the important question. Does the definition, does the decimal expansion always make sense? Is it always valid? Well, the answer is this monotone sequence theorem. As a matter of fact, the decimal expansion like 3, 3.1, 3.14, 3.141, that kind of sequence is increasing sequence, and everything is bounded, as, for example, by 4, so it has converged. I mean, we have increasing sequence, it cannot come back down, it cannot go all the way up to infinity because it's bounded, and then at some point it'll have to stop. Same for decreasing case. And difficult to prove, but it's easy to understand. We're going to call it monotone sequence theorem.